Hello friends and my dear students, I welcome you all to my channel. I hope you are all well and your studies are also going on well. In this video, I am going to start the next chapter, the next concept, the next solid from the chapter of surface areas and volumes, and this is right circular cylinder, which I will abbreviate as RCC. So we will know the key concepts and formulas of the total surface area, lateral surface area, and volume of a solid and hollow RCC. And also we'll discuss about some key things to remember about RCC. So this video is part of the playlist CBSE Maths for class 9 following the textbook of author R.D. Sharma. If you find this video beneficial, then please like it, share it with your friends, and please support me by subscribing to my channel, and do not forget to press the bell icon so that you will be notified by my future videos. Okay, so we will study about the solid right circular cylinder and the formula of its volume, its lateral surface area, and the total surface area. Now, before discussing the formulas, let's try to understand why it is called right circular cylinder. What is a cylinder and why it is circular and why it is right? Okay, so let's quickly understand what is a cylinder. A cylinder is basically has two end faces, two faces which are some polygon. It could also be circular. A shape. Two faces which are parallel to each other, and those faces are usually some polygon or a circle. So those two faces, let's say, can be they can be square. So let's say those two faces must be parallel, and those two faces, the figure should be congruent to each other. So let's say these are, so this is this face, I am considering the face to be a square, and they are parallel to each other. By saying now what does it mean when I say these two faces or planes are parallel to each other? It means that let's say it means that if you take the center, now these two faces must be congruent figures, and their planes are parallel, meaning if you take the center of the two faces, so this is these two centers, then the line joining, let's say the centers are O and P, the line joining the centers of the two faces should be perpendicular to the plane of the two faces. The OP is perpendicular. So if you consider let's say any line, so this the line segment OP is perpendicular to the this face, plane of this face, and also plane of this face. So, and they are at a distance. OP should not be, the length of OP should not be 0, it should be greater than 0. Then you can see in this case the cylinder formed is, this is the cylinder formed. This is the cylinder formed. So you can see the two faces, the faces are also sometimes called bases. The two bases or the two end faces are parallel, and they are, each face is congruent to each other, and they are, in this case, it's a square. It's a square, and obviously the two faces, the planes of the two faces must be parallel. And I'm sorry, it need not the line OP need not be perpendicular to the plane. No, sorry, the line OP need not be perpendicular to the plane of the faces, but the plane of the faces should be parallel to each other. So this is a cylinder. Let's say now this in this cylinder, So this is a in general cylinder. You cannot say this is where the faces are square. You can say it's a square cylinder where the end faces are square. Now let's see what if the base planes or the base faces are circular. Let's say this is one base face which is circular, and obviously the other base or other face end other base or end face will also be the same congruent circle. Let's quickly copy this. Okay, so these two are now these two planes, these two circular planes, in this case the end faces or the bases are circular and they are congruent circles and their planes are parallel. Now so the center of this is O, of this base of this face is O, and the center of this face is P. So then in this scenario, and obviously the distance OP must be greater than 0, and the line OP, that is the line joining the center of the line joining the center of the two base circles need not be perpendicular to the plane of the two faces, that is the plane of these two circles. So the cylinder formed is this. This is the cylinder formed. Now this is a circular cylinder, and we will study right circular cylinder. So this is a circular cylinder. Let's take another example. The end faces could also be a triangle. Let's say the end faces are this triangle. Okay, the other end face should also be same congruent figure. So it should be a same congruent face. So now if you join so basically in the square in this scenario in this case how the cylinder is formed, you just so you see that in this case the two end faces are square, and this cylinder has is formed of 1, 2 and 3 four lateral faces which are rectangular. Let's try to understand the cylinder formed if the two faces or the two bases are triangular. So now if I join the respective vertices of these respective vertices of the two triangles of the bases, in this case the cylinder formed is this. Is this a cylinder? Okay, now if you consider the center, of these two triangles of the bases, and if you join them, that line in this scenario will not be perpendicular to the plane of the triangles. The plane of the base faces or the end faces should be parallel to each other, and as long as the line joining the center of the two bases is not perpendicular to the plane of the base faces, then it is not a right cylinder. Now in this scenario, in this case, the cylinder, the base, you can say it's a triangular cylinder. I don't know whether there is something called triangular cylinder or not. I think it's a prism, but no, prism is something. In prism, the base faces are triangular, but it's a I think right triangular cylinder could be called a prism. I don't know. I will see that. So in this scenario, the base faces are the end faces are triangle, but yet the line joining the center of the two triangles is not perpendicular to the planes of the two faces. So this is not a right cylinder. This is a cylinder, triangular cylinder. Now, what is the meaning of the right? The meaning of the right is that if you join the line joining the center of the two end faces, that line must, if it is parallel to the planes of the faces, then it is called a right cylinder, and it is called right circular cylinder when the base faces or end faces are circular. So now I hope you have understood what is a right circular cylinder. So this is a right circular cylinder where the base or end faces are circle, and the planes of the, so these are the two base faces, end faces, the planes are parallel to each other, and if you join the center, if the line segment OP, which is the line segment joining the center of the two end face circles, that line OP is perpendicular to the plane of the two base faces, and the radius of the circle, the radius of the two circles of the end surfaces or base faces is small r, and the distance between the center, the distance of the line segment OP is basically the length of the cylinder or the height of the cylinder, which is denoted by small h. So let's now focus on right circular cylinder, which I will abbreviate as RCC. So the basic structure is that a right circular cylinder has two circular bases whose planes are parallel to each other. Line joining the center of the circular bases OP is perpendicular to the planes of the bases, that is the circular bases. The centers of the circular bases are at a distance OP, which is denoted by h, which is the height or length of the cylinder. Now the formula, the volume of the cylinder is basically the volume of a cylinder, the volume of in general the volume of a cylinder is equal to the area of the end faces, multiplied by the length or height. So in this case, since the base faces are circle, the area of the circle is pi r square, and the length is h. So the volume is area of the base multiplied by height or length, which is h. So it is pi r square h. So this is the volume of a right circular cylinder with the radius r and height h. So how do you describe a right circular cylinder? What are the dimensions you need? You need the radius, which is basically the radius of the circular end faces or base faces, and the length or height. Okay. Now what is the lateral surface area? The lateral surface area is the, you can see the curved surface, which is the curved surface, and the edge, you can see the edges of the curved surface are along the circumference of the two circles. Two circles means the two base. So this the area of this the lateral surface, that is the area of the curved surface, is known as the lateral surface area, LSA. Its area is 2 pi r h. Now why 2 pi r h? The idea is that so this is the, you can see if you try to visualize the circumference of the two circular bases is 2 pi r, and the height of the RCC is h. So the lateral surface area is 2 pi r h. Now why 2 pi r h? I hope you will be able to visualize the lateral surface area, the curved surface, if you as a rectangle. Consider a rectangle whose length is let's say whose length is whose length is 2 pi r and whose width is h. Let's say there is a rectangle whose length is 2 pi r and whose height is h. Now, if you roll this sheet, consider this as a sheet of rectangular sheet. If you roll this, if you roll this to form a curved surface, then the circumference of the edges, you will see the circumference of the edges will form a circle whose radius will obviously be r. So that is the reason you can consider the curved surface of a lateral curve, the curved surface or the lateral surface of a cylinder RCC as the rectangular sheet. If you unfold it, if you flatten the curved surface area of a curved surface of a RCC, if you flatten it, you will see that it will be a rectangular. It will be a rectangle whose length is 2 pi r and height and width is h. Okay, and so since in this rectangle the area of this rectangle is length into breadth, so it is 2 pi r h. So that is the reason we are having the area of the lateral surface area as 2 pi r h. Now, what is the total surface area or TSA? It is the area. It is the area of the curved surface as well as the two bases or the two end faces. Now, each end face is a circle having area pi r square. So, the total surface area will be 2 into area of base plus LSA. LSA means the lateral surface area, that is the area of the curved surface. So, it will be pi r square is the area of each end face. So, there are two end faces. So, it is 2 into pi r square plus 2 pi r h. If you simplify it, it will be 2 pi r multiplied by r plus h. Now, it is absolutely not necessary to remember this formula. If you can, this is a very simple formula. If you should remember, but if you cannot remember, there is absolutely no reason to panic. You must understand the concept that the total surface area is the area of the curved surface. The area of the curved surface is 2 pi r h. You must understand this, and the area of the two bases, and the area of each base is pi r square. So it will be pi r square plus 2 pi r h. In this way, you can also derive this formula, total surface area. Okay. Now this was about solid RCC, that is solid right circular cylinder. This formula was for solid right circular cylinder. Now a cylinder could also be hollow and having a certain thickness. Now consider this figure, hollow solid RCC, that is hollow solid right circular cylinder. The height is h, that is the length of the center of the two end faces, circular end faces is h. Now since it is hollow and the cylinder has a thickness, we will have two radius. We will have two radius of each end faces, that is the internal radius and the external radius. So in a hollow solid RCC, what dimensions you need? You need the height or length, which is h, and you need the internal radius or the external radius. So external radius will obviously, capital R will be greater than small r, which is internal radius, and the thickness is obviously the thickness of this hollow solid RCC, where the internal radius is small r, external radius is capital R, the thickness is capital R minus small r. So then what will be the volume? Volume of the please note that this is a this is not hollow solid RCC, but this is hollow RCC having a thickness. This is hollow RCC. Okay. Now, what do you mean by the volume of a hollow RCC? It is it will be the external volume minus the internal volume. I hope you will easily understand why the volume of a hollow RCC is equal to the external volume minus internal volume. Now what is external volume? External volume is External volume is the, if you consider the external, if you consider a solid RCC with external having radius equal to external radius, which is small capital R, that is the external volume of a hollow RCC. And what is internal volume of a hollow RCC? If you consider a solid RCC having a radius equal to the internal radius of the hollow RCC, which is small r. So then the volume of the hollow RCC will be external volume minus internal volume, which is equal to pi capital R square h minus pi small r square h. So this is equal to pi h multiplied by capital R square minus small r square. This formula you should remember. Even if you can't remember, you should be easily, the basic concept is that the volume of a hollow RCC is equal to external volume minus internal volume. And what is external volume? External volume is the volume of a solid RCC whose length, whose height is h and whose radius is equal to the external radius of the hollow RCC. And what is internal volume? Internal volume is the volume of a solid RCC whose height is h and whose radius is equal to the internal radius of the hollow RCC. Now, what will be the lateral surface area? Now, it is tricky. The lateral surface, since it is hollow, there are two curved parts. There are two curved surfaces. One is external and one is internal. The external one is, you can, the area of the external curved surface is, you can consider to be equal to the lateral surface area or curved surface area of a solid RCC having radius equal to the external radius, which is capital R. So similarly, the and the internal surface area you can consider that to be equal to the lateral surface area of a solid RCC whose radius is equal to the internal radius, which is small r. So then the effectively the lateral surface area of a hollow RCC will be equal to the external lateral surface, external LSA and the internal LSA. The external LSA is 2 pi capital RH and the internal LSA is 2 pi small rh. So if we simplify, it is 2 pi h multiplied by capital R plus h. Now this formula also, it is not hard and fast rule that you should remember this. You must understand that what exactly is the lateral surface area of a hollow RCC. It is the sum of the external curved surface plus the internal curved surface. What is external curved surface? External curved surface is the curved surface of a solid RCC having radius equal to the capital R, that is external radius of the hollow RCC. And what is internal curved surface? Internal curved surface is the, you can consider it to be the curved surface of a solid RCC having radius equal to the internal radius of the hollow RCC, which is small r. And then if you add them up, if you then the lateral surface of the hollow RCC will be equal to the external LSA plus internal LSA. Okay. Now what is the total surface area? Now the total surface area is basically you have to add the surface area of the two end faces or base faces. Now in this case, what will be the area of the surface area of the one end face? It will each end face is now a kind of this. Each end face. So this is the surface area of each end face or base face, where the internal radius is small r and the external radius is capital R. So the area of the shaded region is the surface area of each end face, which will be obviously equal to pi r square, pi capital R square minus pi small r square. So the area of each end face is equal to pi into capital R square minus small r square. Okay, now see, the total surface area is equal to 2 into area of base. Area of base means area of each end face plus the LSA. LSA we already know is 2 pi h multiplied by capital R plus h. And what will be the area of each end face or base? It is pi capital R square minus pi small r square. If you simplify this, you will get this formula. 2 pi into R plus R multiplied by R minus capital R minus small r plus h. This formula, if you can remember, that is fine, but most probably you won't be able to remember. But always try to understand the basic fundamental concepts, that the total surface area is equal to the area of the curved surface plus the area of the end faces. The area of the curved surface, which is the LSA, you have already found to be this, and then you must know what will be the area of each end face, which is pi into capital R square minus small r square, and then the total surface area will be 2 times the area of end face or base face plus the LSA. Okay, so this was all about the volume, surface area and lateral surface area of a solid RCC and a hollow RCC. RCC means right circular cylinder. Now, few things you must keep in mind regarding problem solving on RCC. Now, okay, the first thing is, for a solid RCC, if you have a solid RCC, you will see that the volume V divided by LSA, V by LSA, you will see it is coming out to be small r by 2. So this implies small r is equal, small r means the radius of the RCC. So radius for a solid RCC, radius is equal to 2 into volume divided by LSA. Now, I also do not expect you to remember this, but just for the sake of discussion, I am mentioning this result. Now, obviously, you know the V, you also know LSA. From there, if you put the formula of V and LSA, you will see it will be R by 2. So the basic concept is that if you are given volume, if you are given the volume of RCC and the LSA of RCC, and if you are asked to find the radius, you should be able to find it. Not using this formula, I am not asking you to remember this formula, but you must be smart enough to do this critical thinking, that if you are given volume and if you are given LSA, from the values from V and LSA, how you will get R. So this derivation you must be able to do it. The second thing is that for a solid RCC, if only the radius is changed to k times. Now the k is basically, definitely k is greater than 0. It is a positive real number, real constant. It could be greater than 1 or less than 1. Basically it is greater than 0. So if radius is changed to k times, how the volume and the LSA are changing. So the volume V1 is the initial original volume where the radius was R and the height was h of the RCC. So V1 is equal to pi r square h, and V2 is the volume of the RCC of the new RCC when the radius is changed to k times. So radius now has become r into k. So V2 is equal to pi into kr whole square h. You will see it is coming out to be k square V1. The small observations and results you must be able to derive very easily. Now, what is LSA? The original LSA was 2 pi rh. Now the new LSA, once the radius smaller has become k into r, the LSA2 you will see is coming out to be k into LSA1. So basically, when in a solid RCC, if the radius is changed to k times, the volume is changing to k square times, and the LSA is changing to k times. Okay. Now see, if only the height is changed to k times, what happens? If only the height is changed to k times, you will see the original volume was pi r square h. The new volume will be pi k into pi r square h, which is k times volume, the original volume. So when in a solid RCC, height is changed to k times, the volume is changed to also k times, whereas if the radius is changed to k times, the volume is changing to k square times. Okay. Now for even the height is changed to k times, let's see how the LSA is changing. So the original LSA is 2 pi RH, and the new LSA will be 2 pi R into kh, which is k times LSA 1. So you can see that if only the height is changed to k times, then both the volume and the LSA are also changing to k times. Now if both the radius and height is changed to k times, what happens? The original volume was pi r square h, and you will see the new volume is V2, the new volume is becoming k cube V1. So for a solid RCC, if the radius and height are both changed to k times, then the volume is changed to k cube times. Now please note, I am saying all over again and again, I am not expecting you to remember all these results, but just know the way you can see the way you should be easily able to find how the volume, LSA or even TSA are changing when the height or the radius are changed to some multiple values, that k times, the radius is changed to k times, or the height is changed to k times, or both radius and height is changed to k times, then how volume and LSA and TSA are changing. You should be able to derive that. Okay. So you can see now the LSA, when both radius and height is changed to k times, the new LSA is becoming equal to k square times the old LSA. So the LSA is becoming k square times, is changed to k square times. Similarly, you will see also that the total surface area is also changing to k square times. Okay. Now this thing is a very conceptual thing. If we consider an inflated tire of a bicycle, the inflated tire of a bicycle, if you are asked to find the volume of an inflated tire of a bicycle, and you are given only two information. One information you will be given is that obviously that the cross section of a tire, inflated tire of a bicycle, is a circle. So this is a cross section, this is a circle, basically this is a circle, and so the radius of the cross section, the circular cross section, the radius of the circular cross section will be given, which is say small r, and the distance of the center of the cross section, the distance of the center, let's say consider this cross section, P is the center of the cross section of the tire. The distance of P from the axle, the point O is the axle of the bicycle, that distance D will be given. That is the distance between the center of the cross section of the tire and the axle, which is OP, will be given, which is D, and the radius of the circular cross section will be given, which is small r. Then you will be asked what is the volume of the inflated tire. The idea is that you can consider this circular tire as a RCC. If you cut this circular inflated tire like this, and if you flatten this, you will see it will become a right circular cylinder. Now then in that case, so and the volume of that RCC will be the volume of the inflated tire. Now obviously, if I visualize this circular tire as a flattened right circular cylinder, let's say, after I have, so this is the RCC, let's say this is the height or length of the RCC, that is the tire when it is cut and flattened. Obviously the two end faces, these two end faces of the RCC will be the same circular cross section of the tire. So obviously then I will know, for the RCC I will know R, which is the radius of the cross section, circular cross section of the tire. Now I need to find h. What will be h? What will be the length of this RCC when this whole tube or tire, inflated tire, is cut and flattened. So that's where this information will come, will be used. That is the D. You can see that the length, the h will actually be the circumference of the dotted circle. Now, what is the dotted circle? If you consider the dotted circle, it is a circle having radius equal to d. And what is this? And the circumference of the dotted circle is actually the length of the RCC, which is h. So h will be equal to 2 pi d, because the radius of the dotted circle is nothing but the distance between the center of the circular cross section of the tire and the axle, which is OP. So now the volume of the inflated tire will be equal to the volume of this RCC, where h is equal to 2 pi d. So I know h, I know r, so I can easily find the volume of the inflated tire, which will be equal to pi r square into the height h is nothing but 2 pi d. So it is 2 pi square r square d. 2 pi square r square d. Now again, I really do not expect you to remember this formula, but you should be able to derive this formula from the fundamental concept. You must be able to visualize that this inflated circular tire as a RCC, if you vertically cut the tire and flatten it, you will see that then if you flatten it, it will look like a RCC, that is right circular cylinder, where the circular end faces will be have area equal to the cross sectional area of the tire, whose radius is given as small r, and the length of the RCC will be equal to 2 pi d. Let's see the next. So another concept is that if you are asked to find the largest RCC formed in a cube of side A, largest means the volume is maximum. What will be the volume of the largest right circular cylinder cut out from a cube of side A? So in this figure you can see one face of the cube, it is circular, it is square of side length A. Now the concept is that the largest RCC cut out from a cube of side A will look something like this. That is, the end faces, the circular end faces of the RCC will obviously lie on the two opposite faces of the cube, and the height and the length will also be equal to the edge length or the side length of the cube. So basically so the height and the length of the RCC, largest RCC, will be equal to A, and what will be the radius? The radius A of the end faces of the RCC, largest RCC, will be equal to side length of the cube divided by 2. So r small r will be equal to A by 2. So now you can easily find the volume of the largest RCC, whose radius will be equal to A by 2 and whose height will be equal to A. So obviously the volume is pi r square h, which is pi A by 2 square A, which is pi A cube by 4. Now again, I really don't expect you to remember this formula, that the volume of the largest RCC cut out from a cube of side length A is equal to pi A cube by 4. No, I really don't expect you to remember this, but you must understand the concept, how the largest RCC is formed in a cube, in a cube of side length A. And of course, so once you know the radius and the height of RCC, you will obviously be able to find out the LSA and TSA. This concept, the fifth one, is little complex. So the earlier one was what will be the volume of the largest RCC that can be cut out from a cube of given side length. This time it is saying what will be the volume of the largest RCC formed in a cuboid of dimension L by B by H, that is length L, breadth B and height H. Now there are, in this case, there is no hard and fast rule, there is no formula, there is no exact one formula using which you can be able to find the volume of the largest RCC that can be cut out from a cuboid of dimension LBH. Actually there are 6 possibilities. You have to compute 6 values. That there are 6 possible RCC that can be cut out from a cuboid, and you have to find the volume of those individual RCC, and whichever is the maximum, you have to consider that RCC to be the largest RCC. Which are those 6 RCCs? Now, so the 6 RCCs can be formed based on which of the opposite faces of the cuboid are considered for the circular basis of the RCC. So you know, in a cuboid there are 6 faces. That is, there are how many faces? 1, 2, 3, 4, 5, 6. There are 3 pairs of opposite faces. So considering each such pair of opposite faces, those 2 opposite faces will actually have the 2 end faces of the RCC. Now if you consider, so let's say if you consider the face, and you know that there are the 6 faces of a cuboid of dimension LBH, they have basically 3 distinct areas, which are LB, BH and LH. If you consider the face of dimension LB, let's say this is the cuboid, so this, let's say this is B, this is L. So if you consider this face and its opposite face, this is the top face and its opposite face, which will be the bottom face for a hall or for a room, which will be the roof and the floor. If you consider those 2 faces, then and those 2 faces whose dimensions are L by B, then those 2 faces will actually contain the end faces of the RCC. Now what will be the radius of the circular end faces of the RCC if we consider the face L by B? Now it will be, if you have a rectangle of dimension L by B, length L and breadth B, what is the largest circle you can draw? What is the largest circle that can be inscribed in this rectangle of length L by B? The diameter of that largest circle will be equal to the smaller side. In this diagram you can see B is smaller than L. So the diameter of the circle, largest circle that can be inscribed in this rectangle, will be equal to B. So this will be the roughly largest circle you can draw. So if you consider the face having dimension L by B, then there are 2 possibilities depending on whichever is larger, L or B. So there are 2 possibilities of finding the R, that is the largest circle that can be inscribed in those faces. In the face of dimension L by B, there are 2 possibilities. If L is greater, we don't know whether I think it has to be between L and B, one will be smaller and one will be larger. So definitely we will consider the smaller smaller, if L is less than B, then obviously the radius of the circle, largest circle will be L, the diameter of the largest circle will be L. So the radius will be L by 2, and the height will be H. The height will be H. So if you consider the two end faces of the RCC, of the largest of the RCC, to lie on the two opposite faces having dimension L by B, then the length or height of the RCC will obviously be H, which is the height of the third dimension of the cuboid. So in this case, so if L is less than B, then obviously the radius of this circle, that is the radius of the circular faces of the RCC, will be equal to L by 2, and height is H. So in that case, volume will be pi L square H by 4. Now it could be the case that L is greater than B, then the radius will be B by 2 and height will be H. In that case, the volume will be pi B square H by 4. So we are having two possibilities, considering the face of the cuboid having dimension L by B. Now in this way, there are three possibilities of choosing a face, choosing two opposite faces where the end faces of the RCC will lie. So the second dimension of the face will be L by H, and in this case also the two possibilities will be, the radius can be either L by 2 or H by 2, and the height will be B. The third dimension is B, so height will be B. So these are the two possibilities of volumes, V3 and V4. Similarly, the third consideration of the two opposite faces of a cuboid, which can be considered where the end faces of the RCC will lie, will have the dimension B by H, and in this case you will see there are two possibilities of creating an RCC, and the volumes will be pi B square L by 4 and pi H square L by 4. So essentially we are having 6 volumes, 6 possible RCCs that you can think of forming or cutting out from a cuboid of dimension LBH. If those two, so these are the 6 volumes, V1, V2, V3, V4, V5, V6, which are basically, you can see they are pi L square H by 4, pi B square H by 4, and then pi L square B by 4, pi H square B by 4, and then pi B square L by 4 and pi H square L by 4. Out of these 6 volumes, whichever is the maximum, that will be the target largest RCC. So this was all about the concepts and formulas of surface areas and volumes of a right circular cylinder, with some additional things to keep in mind. I will not solve any problem in this video. In the next, so the couple of next videos will be on problem solving based on the surface areas and volumes of a right circular cylinder. If this video was beneficial, then please like it, share it with your friends, and please support me by subscribing to my channel, and do not forget to press the bell icon so that you will be notified by my future videos. If you have any query or any question regarding my concept that I have discussed, any formula or anything that I have discussed here, please feel free to let me know in the comment section. I will do my best to help you out. So thanks. So that is all for this video. Please stay tuned for the upcoming videos where I will solve problems on the right circular cylinder of surface areas and volumes. I am ending the video here. Thanks for watching, and until the next video, take care and bye.